Hello, welcome to this lecture series on electronic properties of materials. This is lecture number 11. In this lecture, I am going to discuss limitations of classical free electron theory, that is limitations of Drude theory. Okay, in the last lecture we had discussed about some of the success of Drude model. Okay, and here I am going to show you the limitations, some of the limitations. Okay, yeah. Number one, see the thermal conductivity K, electronic contribution to thermal conductivity K, we have calculated this, or we have derived the expression for K using Drude model, and the expression comes out as 1 by 3 into mean of the square velocity into tau, that is relaxation time, into CV electronic electronic contribution to heat capacity. Okay, and I have told you that the thermal conductivity which we calculate using these datas, okay, it almost matches with the experimental value. Okay, so experimental value and this value are almost close. Okay, so Drude as well as many scientists thought that this expression is okay, right? It is fairly good. But when people calculated the average mean square velocity and the electronic contribution to heat capacity, these values do not agree with the experimental value. For example, the electronic contribution to heat capacity calculated from Drude model, okay, if you compare with the experimental value, right, Drude prediction is almost 100 times greater, okay, than the experimental value. Okay, then second, the mean square velocity calculated from Drude model, if you compare this value with the experimental value, it is almost 100 times lesser than the experimental value. But when we multiply this and this, what happens is that here this value is 100 times lesser than experimental value, this value is 100 times greater than experimental value, so that hundreds get cancelled, so that's why we get almost the values agree with the experimental value. Okay, the K value agrees with the experimental value, but it doesn't mean that this equation works always well. No, listen, because there are some errors, right, available in the calculation of average mean of the square velocity and electronic contribution to heat capacity. Okay, and these two are the main limitations. Though this equation gives K value which is almost good with the experimental value, right, but the values calculated for average square velocity, average of the square velocity and electronic contribution, they do not agree with the experimental value. Clear? Then next important limitation is about Hall coefficient. We have discussed that Hall coefficient RH is equal to 1 by reciprocal of number of free electrons per unit volume into charge of the carrier, If the carrier, suppose if you take metal, according to Drude, okay, free electrons are responsible for conductivity. Okay, therefore the charge carrier in metal is actually electrons, the free electrons, and free electron carry negative charge. Okay, if Drude prediction is correct, then for all the metals the Hall coefficient, since the charge is negative, for all metal Hall coefficient should come out as negative. Yes, it was observed for many metals that the Hall coefficient is negative, but for few metals, metals like beryllium, okay, aluminium, etc., for few metals, the Hall coefficient value was found to be positive. Okay, what is the what is the source for getting this positive value? That could not be explained by Drude model. According to Drude model, free electrons present in the metal are responsible for conduction. Okay, so free electrons are the carriers, right? What is the charge of the electron? Negative. If electron charge is negative, Hall coefficient should also be negative. Yes, it was found that in many metals Hall coefficient is negative only, but for few metals, okay, like beryllium, aluminium, etc., Hall coefficient found to be positive, which could not be explained by Drude model. Okay, this is one important limitation of Drude model, right? Then next one, see the Weidemann-Franz law. Okay, we have calculated this ratio of Weidemann-Franz law using Drude model. So the electronic contribution to heat capacity, thermal conductivity divided by electrical conductivity of the metal measured at the same temperature T. If you take this ratio comes out as 1.11 into 10 power minus 8 as per Drude model. Yes, it is a constant. Okay, so people thought that this model is a successful model. But if you observe the value carefully, the experimental value is actually 2.245 into 10 power minus 8. Right? If you compare these two values, see the Drude prediction is almost half the time the experimental value or experimental constant. Okay, why the value is almost half the time to the experimental value? That could not be explained by a Drude model. Okay, Drude model predicted that this is a constant, good, but this constant is almost half the time the experimental value. What is the reason for that? That could not be explained by Drude model. Okay, then then the last limitation, which is very, very important. See, in Hall effect, you know very well, when you apply when you connect a metal sheet, right, to the two opposite corners to the source of battery, and if you connect a voltmeter, you will get some voltage. It is called longitudinal voltage, right? And if you connect the other opposite ends to another voltmeter, okay, in the absence of magnetic field, external magnetic field, there is no voltage in the transverse direction. But when you apply magnetic field, you will get some voltage, right, in the transverse direction, which we call as transverse voltage or Hall voltage. Okay, so you will get some resistivity in the transverse direction and some resistivity in the longitudinal direction. Okay, listen, it was found that the resistivity in the transverse direction, also called the Hall resistivity, is directly proportional to the external magnetic field strength. If external magnetic field changes, Hall resistivity or transverse resistivity will change, right? Whereas longitudinal resistivity, right, the formula is this: m by n of E square by tau. This is as per Drude theory. So as per Drude theory, the longitudinal resistivity depends only on mass of the electron, charge on the electron, and the tau. It is independent of the external magnetic field strength. There is no B naught here, correct? B naught is not here. So that means we can say that as per Drude theory, the longitudinal resistivity is independent of the external magnetic field. Independent of the external magnetic field. But experiment shows that longitudinal resistivity also depend on the external magnetic field strength. Okay, it also depends on the external magnetic field strength, right? That could not be explained by Drude theory. According to Drude theory, longitudinal resistivity should be independent of external magnetic field. But experiment shows that longitudinal resistivity also depends on the external magnetic field strength. Okay, so these are the few limitations of Drude model, right? In order to overcome these limitations, okay, scientists starts to think about the new model, right? Immediately the introduction of quantum mechanics, okay, a scientist came with a beautiful idea to overcome these defects or limitations, which is none other than Sommerfeld. So we are going to discuss about the Sommerfeld model, okay, of free electrons or the conduction in metals. Okay, how thermal conduction takes place, how electrical conduction takes place in metals. Okay, yeah, I stop here. We'll continue the Sommerfeld model, right, from the next lecture onwards. Okay, thank you for listening.